Hi, we'll start here, the section A of the project P1 on the analysis of a simple logic circuit based on logic gates, but this time using the method 3 of our subject, which consists of developing a handwritten solution using Boole's algebra. Okay? So, for example, this is the circuit that we have in mind, a section of a circuit C, for example, that we call circuit W. So the objective is to obtain its truth table in this way, W as a function of the inputs D1, D0, A and B, so that we can plan the exercise in this way. We have the logic diagram here. This is the circuit to be analyzed. And so on the right side of this picture, we can have at the same level, meaning the same kind of information, we can have the circuit's algebraic equation, which is the circuit based on Boole's algebra. And once we've got the equation, we can go using pen and paper by means of a simple analysis, trying to simplify the equation so that we can find a concept which is extremely important here in this subject, which is called the product of sums, or an equivalent one, which is a sum of products, depending on the way we've gone through this handmade analysis. And this is, an intermediate stage, because if you have the product of sums that we will define now very well, you can go on adding to this sums, the missing variables, so that what you've got is a product of maxterms, which is, exactly the same thing as the truth table, but not as a table, but using an equation. And at the same level, you have the sum of minterms, which is nothing but the sum of products that you may have obtained using a handmade analysis, and the same way, proceeding with the same way, adding the missing variables. So instead of a product, what you've got is a minterm, which is nothing but a product with all the input variables there and ordered correctly. So once you've got the sum of minterms, you have at the same time the product of maxterms and the truth table. So the truth table, or the Carnot map, which is the same thing as the truth table. The truth table is just a table, right? Okay? A way to express the specifications of the circuit. And if instead of a table you like to use an equation, you have both of them. You can use the product of maxterms, all right, taking and ANDing, using an AND, a product this time is an AND, all the terms which are zeros, and you are going to use this way using maxterms. So you can AND all the products, or you can AND all the terms which are zero in the truth table, and those are the maxterms. So you have in the end the product of maxterms, or equivalently, if you have the truth table, you can proceed the same way, but this time taking all the terms which are going to be 1. So you can OR them all. The sum is related to a OR. So you can OR them all, and the terms that you are ORing are nothing but the ones of the truth table, and you represent the ones of the truth table using this convention that we call a minterm, which is nothing but a product, but with all the variables of the input present at the input of. Okay, so this is the idea in P1. Let's go through the analysis of the circuit W. Well, but in general, you may have a large circuit, okay, or something that has a lot of gates organized in one way or another. And perhaps, this is the circuit C. So you are always able to find the output C as a function of D1, D0, A and B. That's for sure, right? But what I'm proposing you is to go step by step instead of attacking the circuit just like that, because it's going to be one of the first ones. Why don't you think about something better, you know, a kind of a strategy? Why don't you go and section this circuit, for example, in two parts? Okay, you can take very well another pen and imagine that here you have, for example, a given circuit, okay, and down there another one. So the big circuit C may be understood as two simpler circuits obtained from the same inputs and ANDed together, you see? So you can go and level the wires if you like. For example, this is going to be the W and this is going to be, I don't know, for example, the Q. Okay? So C, yes, it is this, but the C is also the equation W and Q. So in this way, you can imagine that this big circuit is nothing but the connection of two smaller ones. So if this is, you know, A or D1, if this is D1, D0, A and B, so you are connecting this at the inputs, okay? So D1, D0, A and B, and the same here, right? No problem. So D1, D0, A and B, and then the first section is, you can call it circuit W and the other one circuit Q. Why not, right? So the output W and the output Q go together with an extra and this is the final C. So that is always possible in this subject. If you have a large circuit, there is no problem in doing that kind of thing, and this is okay, because now what you have to handle uh, is not that large, okay? So solving the circuit, I mean that solving the circuit W is not going to be that difficult as solving the circuit C, at least now at the beginning, right? So this is what we are going to do here all the time, trying to find smaller blocks so that they can be easily analyzed, whatever, right? So that's the perfect case. So let's just start, because you know, you see, I'm proposing you starting with the circuit W, this one here, right? Just this section of a circuit. You have a gates, this is a buffer and an inverter like that, okay? And these are driving the gates, NORs and NANDs and ANDs and the like, or whatever, they are different kind of gates. So in the end you have an output W, and as you see in the course, we are going to solve this analysis by means of several methods, okay? So analysis means, you know, analysis means finding the truth table, all right? This is what we have in mind. So let's just start, because here, for example, we can imagine solving this circuit by means of the method 3, which is the Boole algebra, as I explained you before in the first slide. So what we've got here is the circuit, okay, and then on the side we have the equation. This is the same thing, okay? All right, this is the same thing. So we have the drawing of the circuit, but we also have the W as a function of D1 D0, A and B, which is what? Well, if you go and analyze this output, for example, this is A naught, okay, or B naught. This is the output of this gate. Then there is this connection to the D0 naught. So here you have another wire, which is the output of this NAND of two inputs. So the output of this NAND, all right, is nothing but the A naught or B naught, and now and the 0 naught. That's the output of this gate. And so finally you have here another gate, which is D1 naught and A and B and 1. You see, this is all the time a 1, so that's not a problem. You can do that, and then all together not. All right, so if this is the partial result at this wire, in the end it happens that the equation that you are liking to find is something like this. W is going to be A naught, you see this wire W is A naught or B naught and the 0 naught, all right, the 0 naught, all right, and then this is and with the output of the other NAND, which is the 1 naught and B and A and 1. So this is the equation that we are referring here. The equation is the perfect translation of the circuit or logic circuit analysis. So this is the circuit, what you've got here, and on the side there is the equation. So both are exactly the same thing. So now what? What goes next? Well, if you have this equation, or if you have the circuit, you know by the other methods that you can go through a Proteus simulation by means of a virtual laboratory, and you can get the truth table, trying all the possibilities from 0, 0, 0, 0 down to 1, 1, 1, 1. You can do more or less the same if you go using Wolfram Alpha, but this time typing this equation in the Wolfram Alpha engine and solving the circuit or the equation, and in the same way you get the truth table, rearranging perhaps the columns because the engine is going to give you the solution, but perhaps with the input variables disordered. And now this time we have something else in mind, which is going through the solution, which is down there. This is what we want. Okay, this is what we want. We are going to call that the truth table. All right, so what we want is to find in the end the truth table, but now by means of pen and paper and a handwritten analysis. So we will take advantage of the Boole's algebras, theorems and the like. So let's see if we are able from the initial equation to find the final truth table. This is what we are going to do here. In which way? Well, for example, like this, and trying to find, you see here you have a lot of products, so perhaps it's going to be good to find what is called a product of sums. The product of sums, this is POS, that's what is interesting to find here, by means of simplification using algebra. Okay, and then if we have this concept, which is very powerful, as product of sums, we can very well continue transforming this product of sums into something that is going to be called another product, but this time instead of a product of sums it's going to be a product of maxterms. All right, the maxterms are the terms in the two table which are 0, so you can collect them all, and so you have the table as well. So both concepts are perfectly equivalent. All right, but because you do that by hand, if you like, you can generate another concept which is perfectly dual to the product of sums. You have something like a sum of products, right? And the sum of products, SOP, can be in the same way, you know, by means of another simplification. Whatever the way you are going through, you can get product of sums or sum of products. And from these minimized or simpler equations, which are the same as the initial one but simpler, from these equations you can generate, you see, the product of maxterms, or equivalently from the other one, this way you can follow this way and get the sum of minterms. All right, and the sum of minterms is nothing but the sum, you know, or of all the terms in the truth table, which are going to be 1. That's the sum of minterms. So this is also the truth table. So if you like to get the truth table by hand, you can follow this strategy. You see, it's not something that you will do in one step, but perhaps in 2 steps. First of all, from the initial equation, or from the second you get the equation, and from the equation you get the product of sums, and then you do something else to transform the sums into maxterms. And once you've got the maxterms, you already have the truth table, which is what you want in the end. Or in the other way, because that is going to depend on the easiness in simplifying the equation, you can go the same way, simplifying using algebra in order to get something like a sum of products, and then transforming the sum of products into a sum of minterms. And in this way you also have the truth table, right? So now we can do that, all right? Because we have the second, we have the initial equation already here, so there is no problem in trying to get one or the other intermediate solution, so that in the end we can proceed towards the final product of maxterms, right? Okay, so this is the second and this is the equation, right? So in the end there is something missing here, was this final not, and you know that final not was missing as well. So you know this is very tricky. This is why I like to talk to you about this way, because it is very tricky. You know, it is very easy to leave something behind. For example, a final not. So you have A not or B not, and then you have an AND with D0 not, and then there is the final not. And the same here, you have D1 not, because this is the term, you see, D1 not, and then you have the term A and the term B, the literal B, and also a 1, and then a final not. So this is the equation W, right? This is what you like to simplify in some way. Well, the first simplification here is very simple. This one is, you know, very easy to simplify, because if you have x or and 1 and 1 and 1, this is simply x. So there is no need to have this 1 here, right? So now we are going to go through this way. Let's try to see if we can keep this product. You see, this is a product. Okay. So let's see if we can keep this product in 2 terms, but simpler. All right? Something like this. So perhaps what goes next now, if you take this term here, is something like this. You can imagine here that you have x and y and z, you see, and a final not. So this expression is x not or y not or z not. That this and this is the same thing. All right. So we can go like that now, because in this way we can get rid of this large not here. So this is going to be d1 not not, or a not or b. All right, without the big not, b not, that way, right? This is now simplified as well, because you know x not and not again is the same x not not, and this is the same as x. So if you have d1 not not, that is exactly as d1. So you have here a parenthesis, which is this sum, d1 or a naught or b naught. This is what you've got. And this is very simpler. This is what we call a sum, you see? A sum. Because, you know, one variable is missing here. The variable which is missing is the d0, but it's already a sum, you see? So in some way, you are going to this way, a product of sums. Now you have one of them. This is a sum. All right? I mean, reaching to this point, that's the direction where you are going to. So this is the first sum that you've got. So now the other term can be more or less organized in a similar way. So I guess that here something is missing, you know, that what is missing here is this big knot, you know. You see, it is very easy, as I say, to leave behind something. So, and this is why, for example, these kind of exercises are very well solved using the concept of a cooperative group. 2 or 3 people doing the same thing, and let's see if the 3 of them get the same final result, because you see it is very easy to leave something behind and to get something that has errors. So I guess that now this is the right expression. So let's go and do the same thing, because now you can imagine very well, okay, that this is another time the same thing. This is, for example, x and y and everything not together. So this is x not or y not. All right. So we are going to do that now here. This is a not or b not not. All this element is what we considered here x. So x not is what we want, and we will transform this and this and is going to be an or, right? So this is or. Now d0, which is what we call y, but d0 not is what we call y, so now not. So finally this term, okay, happens to be something a not or b, and you see again a double parenthesis is the same as before. It's just x. X not is simply x. So here you are now the possibility to get rid of this parenthesis here. So you have a not or b or d0. So this is the other sum that we are liking to find here. So finally, you see, we've got it. I mean, the equation W has been simplified, so at this level, at this stage, W now becomes what is called, you see, a product of 2 sums. One sum is A naught or B or D0, and the other one, D1 or A naught or B naught, something like this. This is the W, right? The same W that we had at the beginning, but through these, transformations using this kind of stuff from Boole's algebra, okay, postulates and theorems and the like, we get something simpler. So here it is. This is what is called a product of sums. All right? If you like, you can multiply, you can AND it all, A naught, D1. So if you like, you can transform this product into a sum of products. If you like to do that, it's very possible. You are going to have 6 terms or something like that, which are going to be the same as this. But this is okay, because this is, conceptually speaking, this is the product of sums. So now, if we like to find the truth table from this product of sums, what is left here is simply what? Well, add the missing variables in every sum. In this way, you can transform these sums into maxterms if you consider the ordering of the input variables. So this is what you can do now, okay? So let's continue, because now we are here. So now this is also a good time for checking the solution or this intermediate result with your colleagues. This is what the people has to have more or less at this level, okay? So now you can continue solving this problem like this, following this path, okay? From the product of sums to the final truth table expressed as a product of maxterms. This is what you can do now very well. And in which way? Well, following this path, but this means, adding the missing variables. In each sum. And so how it is solved that? Well, applying again one of these theorems that says that if you have x is exactly the same as x or y, you see, and x or y not. This thing is exactly this, this expression is exactly the same as x. But the point now is that instead of a simple x, you have the x plus another variable, y, which do not existed before. So in this way you can go and make it possible to add here the missing variable, which is d0, and here the missing variable is d1, right? So you can do that this way, right? And if you are not sure about that now is the time to check that, okay? Because this is x, well, if you like, you can solve that to be sure that there is exactly this thing is correct. So x and x, or x and y not, or y x, and finally or x or y not. That's the same thing, multiplying everything here, or ANDing everything and ORing everything. So x is simply x, that is right. Even if you have 200 times x, that is x. This is equivalent of having a OR with 3 inputs or 4 inputs. So if you have x, 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 and x, doesn't matter. This is x, right? So then you have x, y not, and then, right, or x, y. So if you like, you can have a common factor, which x, y not, or y. And finally, you have here y not. That's another property which is quite interesting. X and x not is always 0, right? That's the case. The same case as when you have x or 1, right? This is always 1. All right? It doesn't matter the value of x, because this or is always 1. So you can take advantage of this because y or y not is going to be always 0, so that is going to be simplified. All right, and the same case here. If you have y, or let's do it aside, because you know here what you've got is x or x not. X or x not. This is what you've got. So this is all the time 1. Try it. If x is 0 and 0 not, you see, 0 not is 1, so it's always 1. Or if this is 1 or 1 not, this is always 1, you see. So that is what's happening here. This is all the time 1. So you have x or, okay, x and 1. So this is x or x. And finally, as you know, x or x or x or x, doesn't matter the times you like, it's all the time simply x. So that's the demonstration, you see. But you know, complicating the expression this way as a product of two sums, what you've got here is the possibility to do that transformation between a sum and a maxterm. You know, this is what you can do here. So let's try now with the first term. For example, a naught or b or d0. You've got that, right? You agree? You've got that, okay? So now which is the variable that is missing here? Well, dig1. So let's add the dig1. In which way? Well, this is what we call x, all right? So now this is going to be x or y and x or y not. So this is going to be a naught or b or d0 or d1. This is going to be the y, you see. Now, and the same x as before, a naught or b or d0, okay? And finally, or d1 not. That's it. So now what you've got is a sum. It is yet a sum because the variables are not ordered correctly, but now you can arrange that, right? So now it is time for rewriting these terms in the right way. So d1 or d0 or a naught or b, and you know d1 naught or d0 or a naught or b. That's it. This is what we call a maxterm, because it takes all the variables ordered correctly, d1, d0, a and b, as we had stated from the very beginning, right? So now if I make some room here, I can finish that thing, finally obtaining, well, now a couple of maxterms. Which maxterms? Well, this one here, you see, is the maxterm, okay? What? This is d1 with like that, so this is when it has a 0 value, d0, the same. A appears like that, a naught, so this is it is a 1 here in this expression as a maxterm, and then you've got the b, so b is again a regular b, so it is a 0. So this is the maxterm that you've got here, all right? And the other one is going to be, you see, the and with another maxterm, which is d1 not, so this is when you've got a 1 and then a 0, because we are talking about maxterms now, and if the variable appears to be not, it's just a 1, and finally 0. All right, so now you really have two terms from the table which are already maxterms, okay? You've got them. So this is the maxterm 2, and this is the maxterm 10. So you've got two terms of the truth table, all right, which are zeros, the 2 and the 10. And now what? Well, let me take the other expression and let's go the same way, right? Let's do it, for example, down there, in the same place. In this corner is okay. And let's repeat, because now we have something like, well, I had deleted it, so it is going to be something like, let me do it again. So this is going to be D1 not, and A and B not. All right. So the term is this one. This sum is D1 or A naught or B naught. That's the term. All right. So from this term, which is, you know, the sum, you see, we will do the same thing. We will go and add the missing variables, all right? And this time the missing variable is the D0. So this is what we are going to do, to add the D0 variable in this term. In which way? Well, following the same strategy, you know? This term happens to be the same as this, D1 or A naught or B naught or D0, and the same D1 or A naught or B naught or D0 naught. As I said, you can imagine that this sum is X, so this is X or Y, and X or Y naught, exactly the way you see here, right? So now what you've got is two sums again with another variable. So now you have the four of them. So you only have to go through this, rearranging the order of the variables. And this is going to give you this term, D1 or D0 or A naught or B naught. And the other one is going to be D1 or D0 naught or A naught or B naught, right? So now this is what is called a maxterm, because you have all the variables ordered. All the variables ordered. So this is a maxterm, right? So you can represent them like this, M capital and another M capital, because this is another one. So this M capital, you see, because the D1 is literal, it is a 0, because we talk about maxterms. The 0 is another 0. And then you have A, which is not, and B is not. So this is the M 0, 0, 1, 1 in binary, and with the other M, which is 0, 1, 1, and 1, right? So this means now that W, you see, happens to be, you know, the product of four maxterms. The maxterm, you see, this is the maxterm 3 and the maxterm 7. All right, you see that, the maxterm 3 and the maxterm 7. So W is now equal to the maxterm 2, the maxterm 10, and the maxterm 3 and the maxterm 7, right? So this is the solution. This is the truth table, but expressed as a product of maxterms. And you can even do that, you know, in a way which is more compact. W can be expressed as a product, you know, of maxterms, and now you can use only the indexes here. Order it or not, that is not important. The important is the 2, 3, 7, and 10. So that's another way to express the truth table of the second. So what I mean here is that if you've got a second like this, all right, if you've got a second like this, very well, you have already the analysis finished, because what you've got, you see, is a product of 4 maxterms. And now you can finish this exercise organizing the truth table version of the product of maxterms that you've been developing here. So this is D1, D0, A and B, and this is W. So you can go from 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, and the final 4, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1, right? So this is the table, right? Representation. So what you know now from this second is the final solution, as I say, right? So you see a double line just to make clear that this is the truth table. So what I mean now is that you can go annotating every single binary combination. This is the 0, the 1, the 2, the 3, the 4, you see? If you like, you can subdivide the table to make it easy. 4, 5, 6, 7, and another subdivision here. So then this is the 8, binary 9, 10, 1, 0, 1, 0 is the 10, and then the 11, and the 12, the 13, the 14, and the 15. So you've got them all. So now what you know very well through this analysis is this, you see, is that the combination 2, all right, the combination 2, this one is a 0, and the 3 is a 0 as well, and the 7 is another 0, and the combination 10 is a 0. All right, this is what you know from this analysis, which means that what is not a 0 is going to be a 1, because that is the logic, right? So now you know that the other terms, the other 12 terms in the table are going to be 1. This is what you know. So this is the result. And because you know as well now which terms happens to be 1, you can write them as a product of, as a sum of minterms, as if you had developed the expression of a sum of products and you had add the missing variables the same way, but this time in the product section, right? Okay? So a final description of the W is also, you know, this sum of minterms, and this final description is like that. It's going to be a sum of the minterms that you see here, the 0, the 1, not the 2 and the 3, but the 4, the 5, the 6, not the 7, but the 8, the 9, the 11, and finally the 12, the 13, the 14, and the 15 terms. So this is the same solution. All right? Which means that now, instead of, you see, a product of 4 maxterms, you have an expression that can be developed as well, because this is the compact way. So perhaps the final section of this analysis may be now getting the terms corresponding to the sum of minterms, because you know this is nothing but the minterm 0, all right, or the minterm 1, or the minterm 4, you see, and then many more, and the final one, if you like, the minterm 15. So for example, what is the minterm 0? It is D1 and D0 and A and B, right? And because the 0 is 0, 0, 0, 0 in binary, this is it, because it's a minterm, okay? And then the minterm 1. The minterm 1 is nothing but the M, 0, 0, 0, 1 in binary. The minterm 4 is the 0, 1, 0, 0 in binary, and so on. So if this is the minterm 0, The minterm one can be represented as D1 and D0 and DA, sorry, now this is A. You see the variables must be ordered, that's the key point. D1, D0, A and B, but because D1, D0 and A are zeros and we are talking about minterms, you know that here it is a not. So that's the final situation, right? And the same as this one here. This is D1 and D0 and A and B, and because you've got D0, 0, it's not A not, B not. So in this way you can have the 12 terms, minterms. All right. So that's the final result of this analysis using Boole's algebra. You see, you have to go, first of all, guessing the initial equation, which is always the same, and it is attached to a given secant, because if you modify the secant, finally you will have another kind of equation, so this goes together. Once you have a secant, you have an initial equation. Very well. So from this equation now, if you like to go by hand, by a handwritten analysis, you can go and simplify using postulates and theorems of Boole's algebra, so that you get this concept, which is extremely important and will be retaken later when we talk about minimization using minilog and the like. So we will develop the product of sums or sum of products, either way, and then from this intermediate value or result, we will go to the end, to the truth table, by means of adding the missing variable. All right? So in the end, you have that compact expression, which is this one, all the terms which are 1 in the two table, or that one which is the same. W is also the product of the max terms, you know, the 2, the 3, the 7 and the 10. So what is not a minterm is a max term. So those are the solutions of the analysis in whatever way, as the truth table, as a product of max terms, or as a sum of minterms. All right? Okay, so in the end, what is left perhaps is simply to go and compare the solution that you've obtained here by this method 3, the truth table, with the other tables that you found using the method 1 and the method 2, right? That's a possibility now, to be sure that everything is all right. And perhaps what is also interesting here is that you can apply this methodology not for the secant W only, but any other secant. For example, the Q section that was left here, and for the final secant C, or the final secant key, right? Any other secant can be arranged in the same way, using a handmade pen and paper analysis, so that you get this intermediate product of sums or sum of products, and then the final truth table by adding the missing variables in one way or another. All right.